Up until this point, we've looked at really one model of the atom, right? The Thomson plum pudding model or the Thomson chocolate chip cookie dough model of the atom. Prior to that, if you've taken chemistry, you'll know that prior to the Thomson model of the atom, there was the Dalton solid sphere model of the atom, right? Started off as, look, we got an atom. It's like a pool ball, like a marble. The atoms or the atoms may be a little bit different from each other, just like marbles are a little bit different from each other. But in the end, there's nothing inside. The marble is the marble. And then we went to the plum pudding model, which was Thomson's model, that had these electrons floating around in a sea of positive charge. That was a big deal. That was a big deal because it acknowledged the existence of something inside the atom, something smaller than the atom itself. And it acknowledged the existence of charge inside the atom, negative charges, electrons. It was the discovery of the electron. The Rutherford gold foil experiment, though, performed by a guy named Ernest Rutherford and a couple of assistants, Geiger and Marsden. Recognize that name, Geiger? Yeah, same guy. Performed an experiment that took this model of the atom, which was good compared to anything that we had before, took it to a whole new level. It took it to a level that made it look a lot like the model of the atom that we accept today. Not exactly the same. It's not quite perfectly right, but it looks a lot more like our current model of the atom. Let's talk about the experimenter first. Rutherford and his assistants, they had a box. We'll simplify this a little bit, but basically it boils down to they had a box. And inside this box, this lead-lined box, they had some radioactive material. I'm not sure what it was, but it produced alpha particles. It released alpha particles. So it isn't like they had a box of alpha particles. They had a box of something that produced alpha particles. These alpha particles get released out the hole in the box, at the side of the box. Over here, they got this really, really thin layer of gold foil. Like when we're talking about thin, we mean thin. Gold foil is like aluminum foil, except thinner. You guys ever seen gold foil in like baking? You know what I'm talking about? It's like really, really, really thin, way thinner than aluminum foil. It's so thin that if you touch it, it kind of sticks to your finger, right? It'll rip in your finger when you try to pull it off your finger sometimes. It's that thin. Okay? It's really thin gold foil. Now, surrounding this whole thing is a screen. We call it a scintillation screen, but you don't need to worry about that word, scintillation. The screen glows when it's hit by alpha particles. That's what we got to know about this. This screen will glow if an alpha particle hits it. That's going to tell us where the alpha particle hits the screen. So Rutherford and his assistants, two of them, allow these alpha particles to leave this box, and they allow it to hit the gold foil. And they make 3 observations when all of these alpha particles strike the gold foil. The first observation they make is that most of the alpha particles go straight through. And they know that because they hit the screen directly behind where they were coming from. Most of the alpha particles just went straight through. But some of them didn't. Some of the alpha particles, when they hit this gold foil, went through, but were deflected, changed direction. Few of the alpha particles, a big minority, but still a few alpha particles, when they hit that gold foil, bounced back. And again, we knew they bounced back because of where they hit this scintillation screen. So what does this tell us about the atom? Well, first of all, we know that the gold is made up of a bunch of atoms, right? And until this point, those gold atoms would have been a positive charge, the sea of positive charge with a bunch of little electrons floating around inside. Now Rutherford and his assistants are going to come up with a new model of the atom based on the three observations that they made. Tell me, what does the first observation, the fact that most of the alpha particles go straight through, what does that tell them about the interior of the atom? Good. Most of the atom is empty space. To use an analogy here, you've got a football field outside. It's 110 yards long. Let's say we got 110 people, one person on each yard line. Okay, one person each yard all the way down the football field. They're blindfolded. We direct them, these blindfolded people, to directly across the football field. And then we say, one at a time, it's your turn to run across the football field. It's your turn to run across the football field. Most of the people that ran across the football field ended up going straight across the football field. That tells us that there's nothing really to get in their way, right? If most of the people on the football field ran straight across, then there wasn't very much stuff on the football field to get in the way of those people. Most of the atom is empty space. Now, some of the people that were running across the football field made it across, but they got deflected. Their direction changed partway across the football field. What does that tell us? Well, it tells me that something was pushing them away from their straight line path. Something was repelling them away from their straight line path. They wanted to go in a straight line like the rest of them, like most of them did, but something pushed them out of their straight line path. What would repel an alpha particle, a positively charged alpha particle, out of its straight line path? Yeah. So, well, not necessarily a proton, but we didn't know about the existence of protons at that point, right? But we did know about charge. Something that was positively charged would repel an alpha particle out of its straight line path. So there's got to be something small, because most of the atom is empty space. There must be a small, positively charged, we'll call it a nucleus. A small positive something in the middle. Small positively charged nucleus in the middle. But wait, a few of them bounce back. So 110 people running across the football field, 97 of them run straight across. 10 of them change direction. 10 of them get deflected. So there's got to be something that's pushing those 10 guys, 10 people away from a straight line path. 3 of them bounce back. What happened to the 3 of them? They ran into something. They ran into the nucleus, right? When they ran into the nucleus and they bounced back. But wait a second. What does that tell us about the nature of the nucleus? Well, let's say we've got 110 people that are your age, okay, 17, 18 years old, running across the football field. And let's say that nucleus is a little 3-year-old. When you hit that 3-year-old in the middle of a football field, are you going to bounce back? You're going to knock the 3-year-old over and you're going to keep running, right? So what do you know about the thing that's in the middle of the football field? Not necessarily bigger, but heavy. Right? It's heavy. It's dense. I don't want to associate football and football players with density and being dense at all, but this nucleus that's in the middle that's positively charged, it's got to be dense. It's got to be heavy. Otherwise, the alpha particle would have just knocked it out of the way. To bounce back, it's got to hit something that's heavy. All right, so what does our model of the atom look like now? Now, it's certainly not the Dalton solid sphere model because we already had electrons. But it's also not the Thomson plum pudding model of the atom because now we know there's a nucleus. That nucleus is small, it's dense, and it's positive. But we know we have electrons. So where did Rutherford put the electrons? He made them orbit around. They're going around in circles around this small, dense, positively charged nucleus. Sometimes we call this the planetary model of the atom. See why? The plum pudding model of the atom, right? Because it looks like, I've never actually seen plum pudding, but I guess Thomson's model of the atom looks like plum pudding. The planetary model of the atom because it's like planets revolving around the sun, orbiting around the sun. Got it?